So we'll continue with section 6.5 on equilibrium. And this section will introduce the equilibrium constant. So the amount of reactant relative to the amount of products at equilibrium is unique for each reaction at a given temperature. And it is independent of the concentration of the reactants at the beginning of the reaction. So it doesn't matter the amount you start with. If you start with a very little amount of reactant or some of the product already made, the equilibrium will always end up being the same for a given reaction. And so because of that, for the reaction with the generic chemical equation with reactant capital A and capital B, and the product capital C and capital D, and then the lowercase a, b, c, and d are the coefficient. So for a reaction like that, we are able to write an equilibrium constant, because notice how there is a double arrow here that tells you it's reaching an equilibrium. And so we can write an equilibrium constant symbolized by capital K. And the equilibrium constant has this formula, K, and the little c in the subscript here means equilibrium constant in concentration, because there is different ways of writing equilibrium constant, and it could be like gas pressures or other values that give the amount of reactant and product. And C here refers to the fact that we are using concentrations, and we are using concentrations in moles per liter. The brackets here around the formulas of the product and reactant are symbolizing concentration in moles per liter. It's the convention in chemistry that brackets mean its concentration in moles per liter, so molarity, right? So the equilibrium constant formula is that you take the concentrations of the product over the concentration of the reactant. And if we use this generic formula here, it will look like this. It's the concentration of C with exponent lowercase c times the concentration of D with exponent D over the concentration of A with exponent lowercase a times the concentration of B with exponent lowercase b. So this formula can be found in the reference packet. So here we have the reference packet, and the first page of the reference information for Chem 121 has this formula. So notice how everything that is on the upper left corner of this first page pertains to chapter 6, right? With the heat equation, the energy units, the food type, and the kilocalories per gram, depending on the food type. And then equilibrium constant here. You have this formula there in case you need it. So let's see in practice what does it mean. For example, we have this balanced chemical equation where you have nitrogen reacting with oxygen, both in their gaseous phase, in equilibrium with 2 NO. NO is the product. And we see a double arrow indicating an equilibrium. So we can write the equilibrium constant expression, and it's symbolized by K equals. So it was the product concentration over the reactant concentration. So on the numerator, you will want the product concentration, and here it's NO. There is only one product. So you take NO in brackets. Brackets means molarity of NO. And here, the coefficient 2 that is in front of the NO formula in the equation will become an exponent for the concentration. So the coefficient becomes the exponent for the NO concentration over the concentration of the reactants. And here we have two reactants, NO in brackets to indicate concentration of NO times concentration of O2 in brackets. Notice how N2 and O2 do not have any exponent because their coefficients are 1. So a coefficient of 1 doesn't need to be shown. And so that's the equilibrium constant expression for this particular chemical equation. So there's one thing you need to pay attention to is that when you have a solid or a liquid in your chemical equation, their concentrations are considered constant because typically the solid will be in big chunks and the liquids, will be the solvent typically. So their concentrations are not changing that much. And so because of that, their concentrations are omitted from the equilibrium constant expression. So if we look at the example of the equation given below here, so 2NaHCO3 solid is in equilibrium with Na2CO3, also a solid, plus carbon dioxide, a gas, plus water, also a gas. If you take the equilibrium constant of this reaction, you take the concentration of the product on top. And here you would take CO2 in brackets times H2O in brackets. And that's it. You would not use the Na2CO3 because it's a solid and its concentration does not change, is considered a constant. So then it's not shown into the expression of the equilibrium constant. And this would be over the concentration of the reactant. And here the reactant is also a solid, so it's omitted from the equilibrium constant. So then the equilibrium constant for this equation would be just that, concentration of CO2 times concentration of H2O. So let's go through a learning check to practice writing equilibrium constant expressions using those reactions, chemical reactions. So the first reaction is having 2 molecules of CO plus 1 molecule of O2, both in their gas phase, are in equilibrium with 2 molecules of CO2, also a gas. So let's write the equilibrium constant for this chemical equation. So the equilibrium constant is the concentration of the product over the concentration of the reactant. So here in the numerator, we have only one product and it's CO2. So you would put CO2 in brackets. And then the coefficient 2 in front of CO2 will become an exponent for the concentration of CO2. Then it's over the concentrations of reactant. And so it's going to be over concentration of CO, also squared, because the coefficient 2 in front of CO becomes the exponent for the concentration of CO, times the concentration of O2. Here, everything is included in the constant because it's all gases. So whenever you have gases, they are included. Gases, aqueous solutions, gases and aqueous solutions, basically, because liquids and solids are not included. So that would be the expression for this first reaction. Let's look at the second example. 2H2 gas plus O2 gas are in equilibrium with 2H2O gas. So the equilibrium constant will look like this. You take the concentration of the product, and here H2O is the product. So it will be H2O, and it will be squared because we have a coefficient of 2 in front of H2O. So the coefficient of 2 becomes the exponent for the concentration. Over the concentration of H2, also squared because we have a coefficient of 2 in front of H2, times the concentration of O2. And O2 has a coefficient of 1 in front of it, so the concentration is not raised to any exponent. And so that would be the equilibrium constant for that second reaction. The third example, for HCl as a gas plus oxygen, also a gas, are in equilibrium with 2 molecules of water, liquid, plus 2 molecules of Cl2 gas. So the equilibrium constant here will be the concentration of the products. So H2O squared times Cl2 squared. So here, notice how H2O should not be included because it's a liquid. So H2O would not be included in the numerator. Over the concentration of the reactant, so HCl raised to the fourth because we have a coefficient of 4 in front of HCl times H2O times O2, and O2 has a coefficient of 1, so it's kept as it is. So here, as you can see, it's easy to forget that liquids should not be included in the equilibrium constant. So be careful. As you can see, I was about to forget that H2O should not be included in that equilibrium constant because it's a liquid, and liquids are considered having a constant concentration, so they are not included. Liquids and solids.